So we're going to go on and talk about compositing. So now we come to a more tricky situation, which is what are we going to do when we have transparent objects? Because now we're going to have not just a single color per sample, but we're going to have multiple colors per sample. We talked about alpha just briefly when we talked about color, and we're going to talk about it in more detail now to see how this actually works. So alpha you can think of as the opacity at the surface. So if alpha is 1, we're fully opaque. And if alpha is 0, we're fully transparent. And then we have something in between in terms of our transparency. So there's actually two ways to think about it. You can think of it as partially transparent, as drawn here. You can also think of it as a percentage of cover. So in this case, my yellow triangle is still covering 50%, but it's 100% covering 50%. And then not covering the others. So both of these are valid ways to think about the mental model of what's going on when I use alpha to paste a yellow in front of a red. Where do we use alpha? We use it to draw the boundaries of things that we want to be able to composite. So here's a leaf, and we have some boundaries of the leaf so that we can paste it in someplace. Here's a koala bear, and we've got some alpha channel, which is not just black or white, but which is got some edge, right? So these gray values mean it's 50% transparent. So this is happening because it's fluffy hair on the edge. So the most common operator that we use for alpha, there's a whole set of operators, but the most common one is over. So we're going to talk about over. So I have my koala with my alpha, I have my city, and now I have the koala over New York City, right? And over is not a commutative operator. It matters which one goes first. So putting B over A is not the same as A over B. So we're going to talk first about non-premultiplied alpha. I think this is the more intuitive way to think about what's going on. So if I have my B and I want to put it on top of A, or over, I should not say on top because that's a different operator. B, I want to put over A. We have colors. We have red, green, and blue colors for A and red, green, and blue colors for B. And we also have an alpha value for A and an alpha value for B. So those are going to be the last components here. So what's the final color going to be? Well, if B is covering some fraction, then we want to keep that fraction of B. So if the alpha for B was 100%, then we want all B, and we don't want any of the A that was behind. If it's 0%, we want all the A behind. We don't want the B. And if it's some linearly interpolated value in between, right? This equation should look an awful lot like linear interpolation. I got my alpha B and my 1 minus alpha B. So if I want 50%, I want 50% of B, and then I want 50% of whatever was A. But remember, A is not just A. It's A times its alpha value, right? If my A was only 25% coverage, then I don't want the full yellow value. I want 25% of yellow. So these things all multiply together. So we get some compositing operator, which makes reasonably good sense about what's going on. And what do we do with the alpha of this outcoming pixel? Well, we have that percent cover of B, the part that B let through, times the percent cover of A. And then that's our final alpha. So this is an intuitive operator. OpenGL for years has used this particular model for how to do things. And it's, I think, the way that fits better in people's minds. We're gonna see an improvement to this in a little bit. So there's something called pre-multiplied alpha, right? So here we stored our alpha, but this color is the raw color, right? So if this is 50% red, we just stored full red in here and then stored alpha as 50%. In pre-multiplied alpha, we pre-multiply all these things. So in the end color we want, if I'm 50% red, then that's only going to contribute 0.5 here. It's not going to contribute 1. So we're going to multiply that and store it. So now when we store RGBA, we've multiplied this alpha into everything prior in our storage. So here's 50% red. We got a 0.5 here. We got 0.5 in alpha. 75% magenta. This is not darker magenta. This is more transparent magenta, right? Because we have this alpha here. So this is less intuitive for people to think about, but it makes a lot of math and other things work out better. So let's take a look at why it's going to work out better to do it this way. So first of all, the math is cleaner. So here's our colors. And if we want to do non-premultiplied, we had this extra alpha A sticking in here. So this was the part that we passed through from our front object B that we're putting over. And we had this little bit of alpha that was stuck in our equation. If we look at premultiplied, well, premultiplied alpha is going to be down here. And our alpha had this equation here, is what we were doing on our previous slide, right? This was our equation for the color. This was our equation for alpha. Notice they're not quite the same equation. Something comes out a little bit differently between the two. So with premultiplied alpha, we treat the whole thing as a 4-vector. And then we have a single equation. In addition, there's extra operations in here. If you're a real efficiency geek, which all hardware people are when they're trying to figure out how to implement things in hardware, we care whether it's a 2 multiplies and 1 add or 1 multiply and 1 add. I'm not so much about efficiency myself, but I see why people would care if I'm implementing the low-level thing. So that's yet another reason. But it cleans up how we treat with it. We now just have a 4-vector, and we do a single operation, which does the whole thing. I see the questions coming in the chat. Keep putting them there. I'm going to keep going through this, and I'm going to come back and I'm going to answer all the questions when I get done with this section, because I think it's a little bit easier. So go ahead and keep writing questions in if you want, and I'll go back and check them. So another reason we care about this premultiplied alpha is fringing. So here we have a foreground color of our pink poof ball, and we have some foreground alpha, and we're going to put it over the turquoise pool. And fringing, there's some edge here, which doesn't really belong. And this is with no fringing. And I'll get zoomed in to see these. So here's no fringing. This is what we expect. We've got our pink poof ball over our water. And now if we don't use premultiplied alpha, we get this extra fringe around here. This is not what we wanted. This doesn't look like a smooth composite. So why does this occur? So here's our original color image with our original alpha. If we upsample, meaning we try to make a higher resolution thing out of it, what are we going to do for the in-between pixel? For the in-between pixel, when we upsample from our textures or other things, we do bilinear interpolation. So we're going to bilinear interpolate to get color values along this edge. So we're going to now get these partial blue values. And instead of just being fully transparent, fully opaque or fully transparent, we're now going to get these partial opaque, partial transparent. And then we're going to multiply these two things together in our final thing, and we're going to end up with a little fringe when we try to combine these things. If we use the premultiplied over, then our upsampling will behave in a better way. It's going to, the fact, we're not going to end up with doubled interpolation on the different components. And so when we combine these things and we composite, we're going to have less fringe, which is there. So the premultiplied alpha makes the math work out better, so that when we apply the operations with some other stuff going on, in this case upsampling, it works out. So the more intuitive way works when there's not upsampling, but it screws up when you've got upsampling. So premultiplied helps with that. So here's another problem. Suppose we're building bitmaps. So here's my input color on my edge of my leaf. I got green leaf, red background. And I want to say that I'm alpha 1 only on the green leaf, and I'm alpha 0 on the black. So really, we should be ignoring this red. It's fully transparent. It could be red, blue, green, orange. Doesn't make any difference because it's supposed to not be there. But if we just average this down in our bitmap per color channel, we're going to get this sort of yellowish brown color because we average together red and green. And then for our alpha, we've averaged together 0 and 1, and we've gotten gray. So our final value is this sort of brownish yellow, which is maybe not what you would expect if I started with a green leaf plus transparent. Because remember, this is not supposed to be red, it's supposed to be transparent. We're supposed to be ignoring it. If we do it with premultiplied alpha, we get to this green in the end, right? Here's the multiply formula. So this red here disappears because the 0 alpha is pre-multiplied in with the red, so it's stored as just this black color. It's not stored as this red. And we end up with a green value. So another advantage of pre-multiplied alpha. So where do we use this alpha stuff? Okay, leaves are commonplace. Example, there's another rendering with some kind of leaves and alpha using it. I think I'm not going to mention, this is another problem with not trying to use pre-multiplied alpha. But I'm just going to summarize and say there is a lot of advantages to doing this pre-multiplied. So therefore, some systems have switched over. So traditional OpenGL was using the non-premultiplied alpha. Web pages use pre-multiplied alpha. Your WebGL context exists in a web page, so therefore what it needs to output in its depth buffer is pre-multiplied alpha. So if you're trying to use alpha and you're trying to get transparent objects, and indeed you could put a picture or a texture or something on your web page, and if you render with alpha, it'll show up transparent on top of your web page. So you can render your 3D graphics on top of the text or whatever else you have in your web page. That'll all work fine if you set your alphas in the right way. But you need to use the pre-multiplied alphas to get that to work. Let me see where we're at. Okay, so what does our color buffer update look like now for semi-transparent surfaces? So when we're dealing with alpha, not fully opaque surfaces, we're going to have this over operator. And this over operator is going to return the new thing times some fraction of the old thing. And our update color buffer is just going to assign the color to this over operator. Now, where's our depth test? There was no depth test. If you want to deal with alpha properly, you have to turn off the depth test. I just introduced this wonderful depth buffer. It solves all of our what's in front of what. And now I told you if you want transparent objects, yeah, too bad, you can't use it. In fact, that's true. If you want to deal with multiple transparent objects and get them to behave properly, you need to render them in back to front order. So you could do front to back by flipping around the way you do your over. But you essentially, you have to do the sort. Rather than letting the depth buffer doing this sorting for you, if you want to deal with transparent, you have to do the sort first. So if I have opaque objects and transparent objects, we typically do one pass through all of our opaque objects first with the depth buffer on. So this will set up the depth buffer to know what opaque objects are in front of what. And then we disable the depth buffer update. We don't remove the depth buffer because we still want to know which opaque objects might be blocking our transparent objects, but we don't update the depth buffer anymore. And then we render our transparent objects back to front using the over operator. And then we can get everything together. So yeah, you don't have a place to see more on this later. I stole this slide from somebody else. They have another class. We don't have another class. But you can get all of these things together. Now, if you're doing relatively simple things, can you just hack and like render your transparent objects last and don't worry about turning on and off the depth buffer or whatever? Yeah, you can probably get an okay effect. We saw some people did it in this class. I saw several animals that had transparent parts and people were doing it and it looked fine. So do you have to get all of this right? No, not necessarily. Graphics is about whatever looks okay. But in order to get it right, you're going to need to do this sort. So this is the same thing that I just said. So here's combining our opaque. We're going to render the opaque. We're going to have the depth test on. So we're going to check if we pass the depth test. We're going to update the two things. For phase 2 with the semi-transparent, we don't do any updating of the depth buffer, but we still check if we pass the test, right? So the same line here passing the test, but I've removed the Z buffer update line in terms of the way that the algorithm works when we deal with a transparent object.